Let's welcome to the part 2 of the video showing that nice sets forms a sigma algebra. And let's quickly record. Go back. Let's get into the sigma algebra definition. It is a collection of some subsets of X which sits inside power set. Okay, usually power set is all the collection of subsets of X, and is said to be sigma algebra if empty and X belongs to empty set and the whole set X belongs to A and E belongs to A. It has to be, I mean, E complement belongs to M, and it is closed under countable unions, and A belongs to, for suppose A is equal to power set, obviously it makes a sigma algebra, and this is also makes a sigma algebra. And measurable sets, we observe that E belongs to M if and only if E complement belongs to M, and empty set and R also belongs to M. We also show that it is closed under finite unions. It is closed under finite unions. Now we'll work on, okay, since it is closed under finite unions, now our main goal is to show that it is closed under countable unions. So E n's belongs to M. Does it imply union of E n belongs to N, E n belongs to M? That's our goal. So last time we have seen a finite union can be written as some disjoint union, can be written as disjoint union, what I mean very clearly. For suppose e1 e2 and so on up to en or ek belongs to M, then E is equal to union of, sorry, En, we write it down, N is equal to 1 to K, or I is equal to 1 to K, whatever might be. For the time being we just stick to the observation, or N is equal to 1 to K. Okay, fine, it's K, yeah, it's K, and N is equal to 1 to K, sorry for the, and which is equal to union of N is equal to 1 to K, Fk, where Fk's were constructed as F1 is equal to E1, F2 is equal to E2 minus E1, and Fn is equal to En minus union of I is equal to 1 to N minus 1 Ei. In particular, F3 is equal to E3 minus E1 union E2. So, and we can also do it for countable sets also. For suppose you can continue this process. So I'm just saying that if you have a countable union, for suppose E1, E2, and so on, En, and so on belongs to M, then if you take E is equal to union of N is equal to 1 to infinity, which is equal to union of Fn, where Fn's were constructed like this, I'll write it down, Fn's like this. So the disjoint union N is equal to 1 to infinity. So for the time being we just make the disjoint union. This indicates the disjoint union. So now the question comes into the picture is, for me, I want to show E1 union E2 so on up to, our goal is to show En belongs to M. If En belongs to M, does we want to show union N belongs to N, En belongs to M. So that I can say that, say E is equal to union of N belongs to M, En belongs to M. I can just write it down, union of N belongs to M, Fn belongs to M, where Fn's were disjoint sets. So it is enough to show, okay, it is very good idea to work with Fn's, because everything, whatever the tools, everything works with Fn's. Because for suppose M star of A intersection with Fn, sorry, F1 F2 from the previous lecture, which is equal to M star of A intersection with F1 plus M star of A intersection with F2. If you did not watch this video, go to the previous video number 1 and watch it. and then come back to this proof. This is quite an easy proof we are going to do. It's a very short proof. We'll work it out. So it's a good idea. Now we'll exploit it. We'll exploit it and show this belongs to him. So now say m star of a intersection with union n belongs to n fn plus m star of a intersection with n belongs to n fn complement, which is less than m star of a. This is a goal. Keep the goal in mind. This is the goal we are looking for. This is a goal. So m star of, what is m star of a intersection with n belongs to n fn, which is equal to m star of union n belongs to n a intersection with fn. So which is equal to, which is less than, by countable additivity. I am using countable additivity. M star of a intersection with fn. M star of a intersection with fn. Or we can write down in a more precise, okay, for the safe side, less than or equal to is enough. Okay, we can write down equal to also, but I'm just assuming countable subadditivity and using this by additivity, subadditivity. So and so this implies, and observe that, and also observe that this m star of a intersection with union n belongs to n fn whole complement, which is equal to m star of a intersection with n belongs to n a intersection with fn complement, which is less than or equal to n is running from 1 to k. For all k, we can just observe this because these are the monotonicity. We have writing down from the monotonicity. Here I am using the monotonicity property. What does it monotonicity implies? For suppose A is a subset of B. This implies m star of A is less than or equal to m star of B. And for the quick recall, subadditivity means A is a subset of union of A case where k belongs to n. M star of A is less than or equal to summation. We can write down like this. Subadditivity means m star of A, which is less than or equal to summation k is equal to 1 to infinity m star of A. It is also works for finite one. Yeah, this is subadditivity. Quick recallings. So we are at the things. Okay, now let's put it in a right way. So m star of A intersection with union n is equal to 1, n belongs to n, en plus m star of A intersection with union n belongs to n, en complement whole complement will be less than or equal to summation n is equal to 1 to infinity m star of A intersection with en plus m star of n belongs to 1 to k A intersection with E complement. So we need to show this is, our goal is to show this is less than infinity, m star of A. So if we can able to show this quantity is less than m star of A, then we are done. So our goal is to show this is less than m star of A. It is equivalent to saying that equivalently. Sorry. We are using fn's, right? Fn's. Sorry for the fumble. So these are fn's. So equivalent, it is saming as m star of n is equal to 1 to k m star of A intersection with fn plus m star of A intersection, n is equal to 1 to k A intersection with fn complement, which is less than m star of A. So, and observe that here this finite things comes into the picture. Observe it. Observe that f1, f2, and so on fk belongs to M, since each f1 is equal to e1 and f2 is equal to e2 minus e1. Okay, in the last video we have proved all this. For suppose this belongs to M, so union fk will also belongs to M, and at the same time M star of A intersection with union of fk's, which is equal to summation k is equal to 1 to n M star of A intersection with fn fk. So n is equal to 1 to k fn. So now this is same as, for suppose this is equivalently same as, if you look at this term, this I can write it down as M star of A intersection with union of fk's plus M star of A intersection with 1 to k, which is less than A intersection with fn complement, which is less than M star of A, which is less than M star of A. So this is same as, this is exactly same as, it is exactly same as, exactly same as union fk belongs to, union fn belongs to n is equal to 1 to k. Yeah. So where we are, so this is our goal. We have started with this our goal. Okay, this is our goal. We started with this and we just used subadditivity, and we have just used the monotonicity here, and our goal is to work out with the disjoint sets, because which this makes things much more life easy. And I'm working with fn's, where fn's it is looking like this thing, and we have proved this result in the previous video, and we are just implementing it. And here the pause here, this is an end, pause here and try to understand, pause here and try to write it formally, and if possible, and to get a confidence, to get happiness, to be happy, rewrite this proof. To be happy, rewrite, recreate, and recreate, and take away home exercise, Okay, take away exercise. Take away exercise is just to work on okay. First one, M star of E is equal to 0. Show that it is E belongs to M, or a nice set, and try to show that E belongs to M. We have proved explicitly this second one in the last class, but we try to show that as a recall. You can just show that M star of E intersection with union F, which is equal to M star of E plus M star of F. These are the two takeaway simple exercises. You can just do it down and enjoy. So this implies, for suppose this bigger result will imply this also, we can also write down, you can also say that, okay, M star of a countable set, or in particular which is equal to 0. This implies all countable sets are nice sets. So this is also an exercise. It's a simple exercise. See, here we are understanding the idea of nice sets. All countable sets are nice sets. Empty set is nice set. R is nice set. is a nice set. Okay, these are the few simple takeaway exercises. Work it on. Yes, this is a video. Sorry, this is a channel where I will make complex. Okay, don't expect everything smooth from me. Okay, this is a part 2. We have proved the nice sets is a sigma algebra. We'll come up with the next new concept or new idea in the next upcoming videos. Until then, bye, stay safe. Okay, this is the exercise.